Welcome to ChemDoctor, and this is the second video on the playlist that deals with weak acids and weak bases. In the first video that I did, we focused on the activity of a weak acid, the pH of a weak acid, and in this video what we're going to do is focus on what happens when we put a weak base in water. And like in the first video, what we're going to do is compare the classic weak base, which is ammonia, to the classic strong base, which is sodium hydroxide. All right, so let's take a look first at the pH of a sodium hydroxide solution. And remember that there are a number of videos in the playlist that deal with acids and bases that are already uploaded. And so let's summarize the situation with NaOH. If we take NaOH and add it to water, and I'll write the equation this way, it fully ionizes. That's the thing that defines the word strength for a strong acid and or a strong base. So what makes this strong is the fact that when we dissolve it into water, it ionizes to 100%. It ionizes completely. Another term that you're going to hear in your courses is that it dissociates to 100%. So this dissociates to 100%. It ionizes to 100%. It reacts completely. So if we set up an ICE table for this, or the box as I call it, before any reaction, this is the situation that we have. All right, and I've put water in here to indicate that the NaOH is interacting with the water. So you need to remember your basic definitions. All right, the Bronsted-Lowry definition of a base is any substance which can accept a proton in an acid or in a proton transfer reaction. All right, now after the reaction has happened, because this ionizes completely, the compound NaOH is completely dissolved and ionized, and so we've formed, because of the stoichiometry, 1 molar of sodium ion and 1 molar of hydroxide. Now the sodium ion is neutral when it comes to pH, right? This has no effect on pH, so no effect on pH. All right, so no effect on the acidity. So the whole business end of this thing is hydroxide, which is a strong base. Now to find the pH of this, since we're at the level of hydroxide, we are going to find a pOH first by taking minus the log concentration of the hydroxide, and log of 1 is equal to 0. So the pOH of this solution is 0. To find the pH, we're going to take 14 and subtract 0 from it, so the pH of this solution is equal to 14. Okay, now if you're confused where the 14 came from, remember that 14 is equal to the sum of the pH plus pOH plus pOH. All right, so that's where this came from. Now let's look at the situation with ammonia, because this is a weak base. So when I write my acid or my base dissociation reaction, all right, it's going to be the base, and it's not the base itself that's dissociating, it's what the base is reacting with. And since this is an equilibrium reaction, I use my double half arrows. We're going to produce NH4 plus OH minus, and again we're producing some hydroxide here. That's what makes the resulting solution basic. All right, however, unlike the situation with NaOH, this reaction only ionizes to a small extent. That means that we're only going to produce a small percentage of the hydroxide by comparison to the 1 molar solution of sodium hydroxide. Now when we set up our box, before any reaction occurs, all right, we're going to have 1 molar of the ammonia, and we're going to have 0 of the NH4 and 0 of the hydroxide. After the reaction reaches equilibrium, this is going to be 1 molar minus X, this is going to be X, and this is going to be X. So we set up our equation, it'll be X squared, and then remember that we're dealing with small equilibrium constants most of the time in this business, right? You do have to be careful when we get up around 10 to the minus 3, 10 to the minus 4. You've got to watch out for the 5% rule especially, and you also need to pay attention to the initial concentration, because those two things play a part in violating the 5% rule. But we should be fine here. So it's going to be X squared over 1 molar, and then we set that equal to our equilibrium constant. And when we solve for X, we get 0.0042 molar, and that is equal to the concentration of hydroxide, and it's also equal to the concentration of the NH4 plus. All right, now like in the problem with the NaOH, because we have hydroxide, the first thing we're going to find is the pOH by taking minus the log concentration 0.0042. So the pOH for this is 2.37. And then we use the same trick that we used over here, so 14 minus 2.37, so 14 minus 2.37. The pH of this solution is 11.63. And you can see that there's a significant difference between the pH of a 1 molar ammonia solution and the pH of a 1 molar solution of NaOH. All right, the pH of the 1 molar NaOH is significantly more basic than the pH of the 1 molar NH3, and that's because in this equilibrium, the production of the hydroxide is significantly less, because NH3 is a weak base by comparison to hydroxide, and that means that it has a lower affinity. It has less ability to remove a proton from water. All right, now to finish this, what I want to do is come back and talk about some basics of acid-base chemistry, since we have both of these equations here. And what I want to do is remind the viewer about the assignment of acid base and conjugate acid and conjugate base. So let's address the issue with the strong base first. So I'm going to rewrite this equation to show more accurately what's going on here. So we have hydroxide that is reacting with the water to produce hydroxide and water. And I know this looks a little bit funny to the viewer at first, and maybe it's helpful if you draw your Lewis formulas of these molecules that are reacting. Let's see if I can get this better. We have a pair of electrons here. All right, and then we have the water, which is involved, right? Because you got to remember the Bronsted-Lowry definitions. This is a proton transfer reaction, so the hydroxide is actually taking a proton from the water here, and this set of electrons is going to stay with this water molecule, and that's how we end up producing these two products. And you might look at this and go, well, they're the same, but there's actually an exchange that's taken place here. And to go through and label, now this is our base. Notice that water is acting as the acid, and then this molecule here, the new one that forms, right? Because this hydroxide right here that I've marked with the blue arrow, that comes from this thing. That's what turns into this. So this is actually the conjugate base from the reaction, and the H2O is the conjugate acid. Now, if we look at more detail at the ammonia situation, right? So we have NH3, and I'll put a pair of electrons here. We have our H2O. We have our NH4 plus that forms, and we have the hydroxide. So the NH3 is operating as the base. That means our water is operating as the acid. All right, you can see this set of electrons right here takes the H. And that leaves behind this thing. That becomes the hydroxide here. So the hydroxide is our conjugate base. And then the NH3C is abstracting this hydrogen. It takes this hydrogen and becomes NH4 plus. So this is your conjugate acid. So the conjugate acid-base pairs for this reaction here are going to be NH3 / NH4 plus. That's one of the pairs. And the other pair is going to be H2O and OH minus. Okay, and with that I'm going to go ahead and close this video.